October 2025, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 researchers who achieved what had seemed impossible for decades. They demonstrated that quantum behavior, once thought to be reserved for the invisible and the infinitesimally small, can also exist in objects we can see, measure, and even touch. Their experiment not only confirmed that the rules of quantum mechanics are real, but that they can manifest in the macroscopic world. This recognition did not merely validate a theoretical idea. It opened a gateway to a new understanding of reality. We live in a world that appears solid, stable, and logical. Things are where we see them. Objects do not simply appear or vanish. Everything seems to follow clear and consistent rules. But this sense of security, this appearance of normality, collapses when we examine the universe at its smallest scale. At the heart of matter, where atoms and their components reside, reality behaves in a radically different way. Here, in this subatomic world, everything becomes uncertain, imprecise, and diffuse. A particle is not located in any specific place until we measure it. Before that, it simply is, but not as a point in space, rather as a possibility. This is not a metaphor. In quantum physics, what we understand as real does not take a defined shape until we interact with it. The key concept to grasp here is the wave function. Introduced by physicist Erwin Schrödinger in the early 20th century, the wave function does not describe a particle as a tiny ball moving through space, but as a sort of wave that contains all the possible positions it might occupy. This wave does not directly represent matter, but the probabilities of finding that matter at various points in space. What is truly astonishing is that this wave function is not merely a mathematical tool. According to the most widely accepted interpretation, the Copenhagen interpretation, supported among others by Niels Bohr and Werner Heisenberg, the wave function is what actually exists prior to measurement. It is not that the particle is in some unknown location. It is that the particle is not in any specific location at all until it is measured. It exists in a state of superposition, where all possibilities coexist. This concept of superposition is not merely a theoretical artifact. It has been tested and confirmed repeatedly in laboratories around the world. Experiments with electrons, photons, and even large molecules have shown that particles do indeed exist in multiple states simultaneously until observed. These findings push us to reconsider the very structure of information and truth. How do we define what is, when being itself depends on measurement? The implications of this stretch far beyond physics. They touch logic, perception, and even our understanding of consciousness. Imagine an electron inside an atom. According to classical physics, we might expect the electron to orbit the nucleus like a planet orbits the sun. But this is not what happens. What really occurs is that the electron behaves like a diffuse cloud. This cloud has no defined boundary. It contains areas where the electron is more likely to be found, and others where it is less likely. But nowhere is it completely absent. This cloud is the visual representation of its wave function. When we measure the position of the electron, that cloud, that wave, collapses. At that moment, all the possibilities reduce to a single outcome. The electron appears at a specific location. This abrupt transition from uncertainty to certainty is one of the most baffling aspects of quantum mechanics, not because it contradicts our senses, but because it redefines what it means to exist prior to observation. Physicist Max Born proposed that the wave function should be interpreted as a tool of probability. That is, it does not tell us where a particle is, but where it is most likely to be found. But this idea goes far beyond mere statistics. The strange part is that the particle truly does not occupy any defined position until it is measured. It is not our ignorance. It is a fundamental property of nature. This phenomenon applies not only to position, it also affects other properties such as velocity, angular momentum, and spin. All remain undefined, existing only as a collection of potentials until a measurement takes place. It is in that moment, when something or someone interacts with the system, that a single, precise value emerges. That moment is what quantum mechanics calls the collapse of the wave function. And here is where quantum physics defies our intuition. In everyday experience, things simply are. But in the quantum world, things only become real when they are measured. This implies something profound, that reality, in its deepest essence, is not made of solid things, but of waves of possibility. This discovery did not only change physics, it reshaped our very concept of reality. Because if reality is not defined until it is observed, then what exists when no one is looking? This question has haunted physicists and philosophers for over a century, and it still lacks a definitive answer. Some interpretations claim it is the act of observation itself that creates reality. Others suggest that the wave function never collapses, and that all possible outcomes happen in parallel universes. The quantum framework has also sparked intense philosophical debate. Thinkers have questioned whether reality is objective at all, or if observation itself participates in the act of creation. The famous thought experiment of Schrödinger's cat, a creature both alive and dead until someone checks, is not just a curiosity, but a metaphor for how unsettling and profound quantum mechanics can be. Even as experiments grow more precise, the questions they raise become more existential. What we see may not be all that exists, only all we can access. Regardless of which interpretation proves correct, one thing is clear. The quantum world bears no resemblance to the world of our senses. Instead of certainties, it offers probabilities. Instead of clear trajectories, it presents interference, diffraction, and collapse. A world where we cannot say for sure where a particle is until we look for it. And yet, everything that exists, everything we see, everything we touch, everything we are, is made of these strange and diffuse components. Our universe, at its deepest level, is not built upon things. It is built upon possibilities, and those possibilities only take shape when we pay attention. This behavior, so alien to our everyday logic, is not just an academic curiosity. It has real-world implications, from the lasers used in medicine to the chips that process this very information. All of our modern technology relies on quantum principles. The paradox is that, while we depend on these phenomena to live in the contemporary world, we are only just beginning to understand them deeply. Each new discovery reminds us that the universe is not made to be intuitive. It is made to be explored. In the quantum world, some barriers are not what they seem. What is an unbreachable limit in classical physics may simply be another probability in quantum mechanics. This strange ability to cross the impossible without force or shortcuts was long considered a theoretical prediction. Today, we know it not only occurs, but can also manifest in visible systems involving millions of particles. It has been observed, measured, and reproduced. And as we will later explore, it was precisely the experimental confirmation of this phenomenon that earned the most prestigious recognition a scientific discovery can receive: the Nobel Prize in Physics. Imagine a wall standing before you. It is solid, impenetrable, a barrier no person, object, or energy can pass through without breaking it. Now imagine throwing a ball at that wall. It bounces back. You throw it again. It bounces once more. That is what you expect. It is logical. But now, in the quantum world, the unthinkable happens. In an unexpected moment, without breaking the wall or piercing through it like a bullet or beam of light, the ball simply appears on the other side, whole, undetectable in transit, as if it vanished from one side and instantly emerged on the other. This is the tunnel effect. Quantum tunneling is one of the most perplexing and fundamental phenomena in modern physics. According to classical logic, a particle that lacks sufficient energy to overcome a barrier should not be able to pass. But in the quantum universe, the rules change. Here, particles are also waves. And these waves, even when their energy falls short of surpassing a barrier, can extend beyond it. That extension means something very specific and very real. There is a small yet genuine probability that the particle will not be stopped by the wall. It can, quite literally, tunnel through it. This phenomenon is not theoretical. We observe it in nature constantly. One astonishing example is alpha decay in atomic nuclei. Within certain unstable atoms, a cluster of particles is trapped inside the nucleus by intense nuclear forces. They do not have enough energy to escape. And yet, they do. Not because they break the barrier, but because, in their quantum state, a portion of their wave function extends beyond the nucleus. That small part allows for a specific probability that those particles will appear outside. That is how atoms can spontaneously disintegrate. This mechanism is not a rare exception. It is a recurring pattern in the quantum universe. Subatomic particles often operate under conditions that defy energetic expectations. Instead of relying on force, they rely on mathematical probabilities encoded in their wave functions. This gives quantum tunneling a certain elegance, a delicate dance of existence, playing out not through brute energy, but through potential. Where classical physics sees a dead end, quantum mechanics offers a detour. This shift in perspective allows us to glimpse a universe that is far more flexible and less deterministic than once imagined. Russian physicist George Gamow was one of the first to apply the concept of quantum tunneling to nuclear decay. His model explained how confined particles could escape without violating any classical law. The key was not energy, it was probability. In this strange world, barriers are challenged by the mere existence of uncertainty, and it is not limited to atoms. In the vast and frozen regions of interstellar clouds, where thermal energy is almost non-existent, chemical reactions should be impossible. Without heat, atoms cannot come close enough to interact, and yet they do. How? Thanks to quantum tunneling. Even under such frigid conditions, particles find improbable, yet real, pathways to react. Quantum chemistry keeps molecular formation alive, even where thermal logic predicts nothing should occur. Technologically, tunneling has been tamed and utilized. One of the most iconic devices is the scanning tunneling microscope, which does not observe matter using light, but with electrons that tunnel between an extremely sharp tip and a surface. It is so precise that it can image and manipulate individual atoms. Without tunneling, this tool, which ushered in a new era in nanotechnology, would not exist. Another case is the tunnel diode, an electronic component that exploits this phenomenon to allow electrons to cross barriers under conditions that would normally forbid it. Though its use has been partly replaced by other technologies, it remains a living example of how quantum tunneling is part of real-world circuitry. But how does this physical miracle occur? To understand it, let us return to the wave function. when a particle approaches a barrier, its wave function does not abruptly stop. It diminishes, yes, but it continues beyond the wall. That portion of the wave, however faint, means the particle has a non-zero probability of existing on the other side. It is as if reality itself were unaware it was meant to follow classical logic. The taller or wider the barrier, the lower the probability of tunneling. But it is never zero. That is what makes this phenomenon so unsettling. It breaks no laws, but it defies all intuition. The tunnel effect was formalized by Friedrich Hund in the 1920s while studying electron behavior in molecules. What began as a mathematical idea became a cornerstone of modern physics. A decade later, Brian Josephson applied this principle to superconducting systems, predicting that pairs of electrons could tunnel between materials separated by an insulating layer. His prediction was so revolutionary that, when it was confirmed in the lab, it earned him the Nobel Prize in Physics in 1973. Quantum tunneling, then, is not just a curiosity reserved for laboratories. It is a reminder that nature does not conform to our expectations. There are hidden paths, improbable yet real, paths that only reveal themselves when we look at the universe with enough precision to detect them. This precision is becoming increasingly accessible. Quantum devices are now pushing boundaries not only in physics labs, but also in commercial technology. Scientists and engineers are developing quantum sensors, quantum computers, and even quantum communication systems, all of which, at some level, rely on tunneling. As we refine our tools and deepen our understanding, it becomes ever clearer that the quantum world is not just a theoretical space. It is the foundation of everything we build and innovate. Recognizing this allows us to integrate quantum thinking into the fabric of our technological future. In the coming chapters, we will discover that this phenomenon, once thought confined to the atomic realm, can extend much further. So far, in fact, that even visible objects, composed of millions of particles, can cross their own barriers. Under the lens of quantum mechanics, the impossible is not always so. For decades, quantum physics was seen as a separate universe, a set of rules valid only for the very small. Electrons, photons, atoms, a world governed by uncertainty and probability, where a particle could exist in several places at once, tunnel through walls, or simply not exist until someone observed it. It seemed clear that these rules did not apply to our everyday world. No one had ever seen a chair in superposition, or a cat vanish by simply looking away. But what if the differences were not so absolute? What if the classical world were merely an illusion, built upon layers of collective quantum behavior? That was the question that drove the scientists, who, decades later, would receive the 2025 Nobel Prize in Physics. Their work addressed a fundamental mystery. Why do we not observe quantum effects at large scales? Why do we not see a football in two places at once, even though it is made of atoms that can do precisely that? In the 1950s, physicists John Bardeen, Leon Cooper, and John Robert Schrieffer solved one of the oldest riddles in science: superconductivity. They discovered that at extremely low temperatures, electrons in certain materials stop behaving as individual particles and begin to move collectively. They form what we now call Cooper pairs, a kind of synchronized dance of electrons that act as a single quantum entity. This collective dance was more than a technical curiosity. It was a glimpse into the hidden unity of matter. The behavior of countless electrons merging into one coherent state hinted at a deeper order beneath apparent chaos. It suggested that individuality itself might dissolve at extreme scales, that under the right conditions, particles could forget their separateness and behave as a single, shared identity of energy. This phenomenon allows electrical current to flow without resistance, without losing energy. But beyond its technical usefulness, it held a deeper, more unsettling possibility. What if those millions of electrons were not just an ordered ensemble, but a single quantum thing? What if that entire system could enter a state of superposition? To test this, researchers worked with a device known as a Josephson junction, two superconducting materials separated by a thin insulating layer. In theory, Cooper pairs should not be able to cross that barrier, but in practice they do, thanks to quantum tunneling. That prediction was made by Brian Josephson in 1962, earning him a Nobel Prize a decade later. But the experiment we focus on went even further. It was not merely about watching a few electrons cross the barrier. It was about discovering whether the entire system, composed of millions of Cooper pairs, could behave as a single macroscopic wave function, a giant quantum entity. And they succeeded. The team, led by John Clark, Michel Devoret, and John M. Martinez, designed an experiment with near-perfect precision. They cooled their system to temperatures lower than those found in interstellar space and isolated it from any external disturbances. Under these extreme conditions, the system displayed behavior that could not be explained by any classical theory. The wave function, the iconic symbol of the quantum world, no longer belonged to a single electron, but to an entire circuit. This was a historic moment. For the first time, humanity observed clearly how a tangible object, visible under an optical microscope, obeyed the same rules we once believed applied only to the invisible. The boundary between the microscopic and the macroscopic, between quantum and classical, had just been broken. At the core of the experiment was an ultra-sensitive Josephson junction, designed to act like a potential well, where the quantum system could become trapped, like a ball resting at the bottom of a valley. As the current was gradually increased, that ball was expected to escape its confinement. But the key was in how it escaped. At higher temperatures, the escape could be explained by thermal fluctuations. However, as the temperature was reduced, those fluctuations disappeared, and yet the system continued to escape. Only one explanation remained. The wave function of the circuit was tunneling. As a single quantum object, this behavior was measured thousands of times. The consistency of the results eliminated all doubt. What had once been mere theory was now confirmed as experimental fact. The implications of this breakthrough were staggering. It bridged the gap between the invisible quantum world and the macroscopic realm we inhabit. If entire circuits could exhibit quantum behavior, then perhaps quantum rules are not exceptions, but universal laws hidden beneath thermal noise and human perception. What had seemed like two realities, one quantum, one classical, might simply be different faces of the same indivisible universe. In that small laboratory, under extreme conditions, the universe revealed something profound. Quantum physics has no size limit. In 1935, the physicist Erwin Schrödinger proposed one of the most famous and disturbing thought experiments in the history of science. His idea was simple, yet devastating. Imagine a cat locked in a box alongside a mechanism triggered by the quantum behavior of a single particle. If the particle decays, the mechanism releases poison, and the cat dies. If it does not, the cat lives. But as long as the box remains closed and the system unobserved, quantum physics states that the particle, is in a superposition of states, decayed and not decayed. Therefore, the cat would be alive and dead at the same time. Schrödinger did not devise this thought experiment to celebrate the elegance of quantum theory, but to expose its apparent absurdity. His goal was to challenge the dominant interpretation of the time, the Copenhagen interpretation. How could such a paradoxical theory apply to a living being, to an animal, to a complex organism? Where, then, was the boundary between the quantum and the classical? For decades, the image of Schrödinger's cat symbolized the blurred limits between the microscopic world, where superposition is expected, and the macroscopic world, where classical logic reigns. Schrödinger's cat could not exist in any real sense, or so we thought. But what once appeared to be a philosophical riddle began to lose its impossibility when scientists began constructing systems delicate enough to maintain quantum states in larger objects. What had previously only been observed in individual particles began to appear in complex structures made up of millions of particles. The key was control. For a macroscopic system to remain in a state of superposition, it must be completely isolated from its surroundings. The slightest exchange of energy, vibration, or information with the outside world causes the wave function to collapse. This very principle guided the experiments of Clark, Deveray, and Martinis. By constructing an exceptionally clean superconducting circuit, cooled to temperatures close to absolute zero and shielded from any external disturbance, they succeeded in maintaining a coherent quantum state at a visible scale. The variable they studied was not an isolated particle, but a collective phase difference shared by millions of electrons. That phase difference could exist in more than one value simultaneously. In other words, the system was in a macroscopic superposition. This moment signified more than a technical milestone. It was a philosophical earthquake. For the first time, the boundaries between abstract quantum possibility and tangible engineered reality had collapsed. The Schrödinger's cat metaphor was no longer confined to classroom debates or philosophical speculation. Scientists had given it a body, a measurable form, and a context grounded in empirical precision. This meant that the superposition was not just an artifact of equations, nor a trick of interpretation, but something we could now manufacture and study under strict laboratory conditions. In doing so, we had forced quantum strangeness into the light, into the realm of circuits and instruments. We had built a creature of paradox, not to observe its death, but to prove that quantum indeterminacy can survive at scales visible to the human eye. Instead of a cat both alive and dead, what we had was a quantum circuit in two states at once. And although it was neither furry nor meowing, it represented something deeply unsettling. A visible, manipulable object, crafted by human hands, behaving like a wave function. For the first time, a real-world analog of Schrödinger's thought experiment had been created. The system would only choose a state when measured by the researchers. Before that, the phase difference had no defined value. It was as if the circuit was suspended in a kind of quantum limbo, a physical ambiguity resolved only through observation. This achievement is no small feat, demonstrating that a macroscopic property, not of an electron, but of an entire circuit, can exist in superposition means that the laws of quantum mechanics have no size limit, only strict conditions. The distinction between microscopic and macroscopic is not a natural boundary, but a matter of isolation, temperature, and precision. It is a technological limit, not a conceptual one. The experiment did more than bring Schrödinger's paradox closer to reality. It revealed something even deeper. The universe does not discriminate between small and large, when it comes to its most fundamental laws. If we build carefully enough, we can make quantum phenomena appear at human scale. And that, in itself, changes everything. For decades, physicists imagined what it would be like to capture a quantum phenomenon within the everyday world. But imagination was not enough. It had to be demonstrated. The precise conditions had to be created, so extreme, so delicate, that the impossible would cease to be a hypothesis and become a result. And that is precisely what John Clark, Michel Devereux, and John M. Martinez achieved, earning them the 2025 Nobel Prize in Physics. Their mission was bold: to design a system large enough to be observed with ordinary instruments, yet still capable of behaving as a single quantum object. In simple terms, they sought to demonstrate that a system composed of millions of electrons could cross a barrier, not by touching it, not by breaking through it, not by using classical means, but by tunneling through it. They aimed to observe quantum tunneling at a macroscopic scale. At the heart of their experiment was a Josephson junction, a component made from two superconducting materials separated by an ultra-thin insulating layer. Under normal conditions, that barrier would block the flow of current. But when the materials are in a superconducting state, electrons form what are called Cooper pairs. These pairs act as a single collective quantum entity, a kind of superparticle capable of tunneling through the barrier. But the scientists were not interested in the isolated passage of a few pairs. They wanted to see whether the entire system, the full wave function of millions of electrons, could tunnel through the barrier as one unified block. To achieve this, they had to eliminate every external disturbance. Even the slightest light, heat, or environmental vibration could destroy quantum coherence. They employed a dilution refrigerator, a device capable of cooling the system to just a few thousandths of a degree above absolute zero. That is colder than the temperature of deep space. They surrounded the entire experiment with multiple layers of magnetic shielding, microwave filters, and extreme electromagnetic isolation. In that total silence, the circuit stood alone. No interference, no contact with the outside world. As they applied current to the system, they observed how the Josephson junction responded. At low intensities, the Cooper pairs flowed without generating voltage, exactly as superconductivity predicted. But as the current neared a critical point, something unexpected occurred. A sudden voltage appeared. This voltage was not continuous, nor caused by thermal noise. It was a quantum jump. The system's wave function had escaped its confinement. It had crossed the potential well, as if it did not exist. But how could they be sure this was not simply a thermal effect? After all, at certain temperatures, energy fluctuations can allow a classical system to jump over a barrier. This is where one of the experiment's most brilliant aspects comes in. They repeated the measurements at different temperatures. As they cooled the system further, the number of times voltage appeared should have decreased, if the phenomenon were thermal. But eventually, the escape rate stopped depending on temperature. The system continued to tunnel even in the deepest cold, where thermal jolts were impossible. There was no doubt left. They were observing true macroscopic quantum tunneling. The wave function of an entire system, composed of millions of electrons, was crossing a barrier without the energy to do so, because quantum rules permitted it. What this experiment shattered was not just a theoretical barrier, but a conceptual one. For over a century, the quantum realm was believed to belong exclusively to the microscopic, a world inaccessible to the human scale. But here, in a carefully crafted circuit, built by human hands, we saw the rules of the subatomic stretch their reach. It meant that the separation between the quantum and the classical was never fundamental. It was a boundary imposed by our technological limitations, not by nature itself. The moment this barrier was crossed, physics entered a new domain, one where quantum behavior could become not just observable, but engineerable. And from this, an entire future of quantum technologies begins to emerge, grounded in a single, measurable, macroscopic leap. This result was revolutionary, not only because it proved that the principles of quantum mechanics apply on a large scale, but because it did so in a controlled, reproducible, and measurable way. The experiment was repeated thousands of times, and each time, nature responded the same way, with an impossible jump that only quantum theory could explain. This milestone not only earned them the Nobel Prize in Physics, it also laid the foundation for a new field altogether, the engineering of macroscopic quantum systems. From that moment on, building technology based on superposition and quantum tunneling was no longer just theoretical speculation. It became a discipline of precision engineering. And it all began with a circuit, a barrier, and a jump that defied logic. The experiment that won the Nobel Prize in Physics in the year 2025 did more than confirm that quantum behavior can manifest at macroscopic scales. It demonstrated that it is now possible to build systems that emulate atoms, structures with entirely designed quantum behaviors. These systems, known as artificial atoms, represent one of the most promising frontiers in technological advancement. An artificial atom is not a perfect replica of a natural one. Rather, it is a human-engineered structure designed to have discrete energy levels, much like the electrons in an atom, but with a precision and level of control that nature never offered. In practice, this is achieved using a superconducting circuit that behaves like a two-level quantum system. This is precisely the system that has become the foundation of a new fundamental unit, the qubit. A qubit is to a bit what quantum superposition is to classical certainty. While a classical bit can only exist in a state of 0 or 1, a qubit can exist in both states simultaneously. This means that instead of processing a single instruction step by step as traditional computers do, a quantum computer can explore multiple possibilities at the same time. Here is where the 2025 Nobel Prize takes on an entirely new dimension. The systems used in the award-winning experiment are based on the exact same principles that underpin superconducting qubits. The circuits that successfully maintain quantum coherence at large scales are, in fact, the building blocks for the first functional quantum computers. Controlling quantum tunneling and superposition in these circuits is not just a theoretical triumph. It lies at the very heart of a technological revolution. Just as natural atoms led us into the electronic age, artificial atoms are now guiding us into the quantum era. This revolution in quantum engineering does not unfold in isolation. It is intrinsically linked to one of the greatest scientific narratives of our time, the unification of fundamental understanding with practical application. For centuries, physics sought to describe nature. Today, it seeks to shape it. Artificial atoms are a perfect embodiment of this shift, where the laboratory is no longer just a place of observation, but a space of controlled creation. What makes this moment even more extraordinary is the unprecedented level of customization now possible. Engineers and physicists can adjust the parameters of artificial atoms with such accuracy that they can craft entirely new quantum behaviors, ones that don't even exist in the natural world. These include qubits with enhanced coherence times, variable coupling strengths, or even properties that enable error correction, a critical requirement for scalable quantum computing. Such developments mean that we are entering a phase where natural is no longer a limitation. If traditional atoms are bound by the rules of the periodic table, artificial atoms are limited only by imagination and precision. This freedom marks a turning point. It transforms how we think about computation, information, and ultimately, the physical laws themselves. But the impact goes far beyond mere computational speed. Qubits open doors to previously unthinkable possibilities. Simulations of complex molecules, unbreakable cryptographic systems, and ultra-sensitive sensors capable of detecting the tiniest shifts in magnetic, gravitational, or electric fields. The mastery of these systems is not simply a technological advantage. It represents a profound shift in how we relate to the fundamental laws of nature. Across the globe, governments, universities, and private companies are investing billions in developing scalable, functional quantum platforms. And at the heart of this global race are devices inspired by the Nobel-winning work, systems that do not merely obey the rules of quantum mechanics, but are engineered to exploit them deliberately and efficiently. In other words, we are no longer just observers of quantum physics. We have become its programmers. For the first time in human history, we are not merely deciphering the behaviors of matter at its most fundamental level. We are beginning to design and build matter that responds directly to those quantum principles. The boundary between understanding and creation is beginning to dissolve. And all signs suggest that, in the coming decades, quantum mechanics will cease to be merely a field of theoretical exploration. It will become a central tool of everyday life, embedded in our communications, our medicine, our industries, and even our understanding of ourselves. After witnessing how an entire circuit can exist in two simultaneous states and tunnel through a barrier, a pressing question naturally arises. Why don't we see these quantum effects in the world around us? At first glance, there is no superposition. Things either are or aren't. Objects fall, break, move, but always in a defined, predictable manner. There are no chairs in two places at once, no half-alive cats. Everything appears to obey classical laws. And yet, if what happens at the microscopic level can also happen at the macroscopic level, why don't we observe it? This question has divided physicists since the birth of quantum mechanics. For many, there is no strict boundary within the theory itself. Everything follows the same fundamental rules. The difference lies in how extremely difficult it is to maintain a quantum state on a large scale. It's not that nature forbids it. It's just that preventing contact with the surrounding environment is incredibly complex. That contact causes what's known as decoherence, the natural collapse of superposition due to interactions with other particles, fields, or systems. In other words, quantum behavior doesn't disappear. It simply becomes invisible beneath the noise and complexity of the macroscopic world. Like a delicate painting losing its color after prolonged exposure to air. Still, this explanation doesn't fully settle the debate. There are multiple interpretations of how and when a wave function collapses. Some propose that even a minimal physical interaction is enough to do it. Others believe it is the consciousness of the observer that causes the collapse. And then, there are those who argue that the wave function never collapses at all, that every possibility plays out in a separate parallel universe. This last view, known as the many worlds interpretation, has gained popularity in recent decades, though it remains deeply controversial. What's indisputable is that the experiment recognized by the 2025 Nobel Prize in Physics has forced scientists to reconsider where the line between quantum and classical really lies. What was once considered a natural boundary is now seen as a technological one. If we manage to cool, isolate, and control a system with extraordinary precision, even large-scale objects can exhibit quantum behavior. But this possibility raises further questions. If everything is inherently quantum, then what does the reality we experience truly represent? Is it merely an averaged-out version of a universe where every possibility continues to unfold, hidden in some distant corner of existence? This raises another fundamental question that continues to challenge physicists and philosophers alike. Is classical reality merely an emergent phenomenon? Some theories propose that what we perceive as stability and determinism may actually be the result of a constant averaging of countless quantum interactions. Reality, in this sense, would not be a fixed structure, but a dynamic result of hidden processes occurring beneath the threshold of perception. If this is the case, then what we call the classical world may simply be a convenient illusion, a useful approximation of something far more complex. Quantum mechanics is no longer just a theory about atoms. It has become a framework for understanding the universe, a lens through which reality itself can be examined. And yet, we still don't know how far its reach extends. Could a human being exist in a state of superposition? Could history itself split into multiple coexisting realities? One of the most intriguing aspects of this conversation is the role that scale appears to play. Is there a size, a level of complexity, or a particle count at which quantum effects fade into classical certainty? Physics does not yet offer a definitive answer. What we do know is this: the larger a system is, the more sensitive it becomes to decoherence. It's like trying to balance a needle on its tip. The bigger it is, the more susceptible it is to even the slightest disturbance. And yet, recent experiments have shown that this boundary is not insurmountable. In laboratories of unprecedented precision, scientists have achieved superposition in objects that far exceed atomic scales, including complex molecules and even tiny crystals. The challenge is no longer purely technical. It is conceptual. How do we reshape our worldview if even mechanical systems made up of millions of atoms can vibrate in multiple states at once? These discoveries have reignited the debate over the future of quantum mechanics. Will we need a deeper theory to explain why our daily experience is so decisively classical? Or are we simply beginning to notice what's always been there, veiled beneath the static of the environment? For now, those questions remain open. But with every experiment, every circuit that defies a classical barrier, we move one step closer to an answer. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.